Hi, welcome back. So we're in Chapter 6, Prediction by RCC at the outline, Prediction by classification, to discuss the second step, the logistic regression. So what we're going to do now, we're going to take this problem and reduce the dimension just by taking one variable, say x1, and we're going to look at the problem from that perspective. We know that the line is going to be separable here. It's not possible. So what we want we want to smash this line in a different shape, maybe an unlinear line, maybe looks like this, whereby I could interpret that everything on the side of this line is going to belong to this class. Everything on the side of the line belong to this class. In this region of the line, it's going to take a simple probability based on a threshold. For example, I could put the 0.5. If the value it's somewhere around here, then it's belong to this class. If the value is somewhere around here, then it is belong to this class. What is the task? The task is to design this line. What we need to visit once again, the idea of odd and probability. I mean, these two terms you should be quite a bit familiar with so far. Probability of an event to occur in a very simple form, a basic form, the total number of possible success that had occurred in the past divided by everything that happened before. Say, for example, if I'm trying to find out the probability of team winning a game, I could look at their previous history of 10 different games they played. I know that they have 3 winning and 7 losing. According to this interpretation of probability, well, I could say probability of success will be 3 divided by the total of games they have played. This is my probability of the team winning the game. Now, what the odd says, what we are admiring to happen, team is winning the game, divided by is the opposite of what we admire, which is total of A minus S in this case, 3/7. Now, if I want to bring these two terminology all together by saying, well, can I find the odd of something given that I know the probability? I think from what we are seeing here, it is possible to do that. The odd, if I take the probability of something divided by 1 minus the probability, it is going to give me the odd. I hope the idea or the relation between odd and probability is quite a bit clear to you. Since we are dealing with a binary kind of a case here, y is just 2 possible value. Well, I could consider this class and this class to be something between 0 and 1, and this is 0.5 is the threshold. While I'm trying to transfer this line into this line, this intuitive idea could lead me to find out a principle in mathematics. It helps me to actually make the transformation occur, and that's exactly why we are actually borrowing the concept of probability and odd to actually transfer value between 0 and 1, so to speak. Now, one thing we could do here, if we take a log of an odd, this is known as the log it. Now, what I want to do to transfer this y from being just only 2 value of 0 and 1, it to become into a ratio between 0 and 1. So since when I'm talking about probability, the linear equation that we've been talking about so far, that is just alpha 0 plus alpha 1 x1, which we want to transfer to be a nonlinear shape, I would take the probability or the log of the odd of this particular equation. Now from here, what I can do some algebraic manipulation. This is called the sigmoid function. If I plug values of x, given of course parameter of alpha 0 and alpha 1, the line will be smashed off into a different form, either by this shape or by this shape. So in other words, if I change this term to be positive, the shape will be just like that. If I change this to negative, the shape will be like that. Plug in this using Python, maybe the idea will be better to clarify then. Well, the y value, it's exactly the function we've been talking about just now. This term is going to be minus term. If I run this, actually, I will end up with the S shape that I'm talking about. If I remove this negative term, look at the shape, how it's going to actually flip on the other side. So I am able now to manipulate this shape in a very different way. One more thing, you can actually manipulate the shifting part of the shape. For example, if I would have to change this value to be maybe larger a little bit, you will see that the shape changes in a completely different way. So if I change also bigger value of alpha 1, we're going to see the line is going to be steeper. To shape this line as much as we like depends on our data point. I can transfer this even into 2-dimension by taking the exact same idea here. Everything above this plane is going to be belong to this class. Below this is going to be belong to this class. This is the idea. Once again, this f of x is going to go through a kind of a sigmoid function, whereby the value will be spelled out from this sigmoid function. It will be a probability between 0 and 1. And based on this probability 0 and 1, I can decide a label. And why is that important? This point, imagine them just projected on this squeezed line here, whereby the threshold find out this point belong to this class and this point belong to the other class. I hope the idea now is quite clear to you. So step 1 is done. In the second step, we need to design a loss function. The best way to do this loss function, it turns out, by using something called the negative log of the likelihood function. Well, now if you go back to the Pernoil distribution we were talking about, I have a probability of something. I am guessing the probability, and I have the complement of this probability. Now, when I pick a point, guessing the label, I hope for the following. It is a class 1 if the label is y star. I hope to guess it as C2 if the actual class is 1 minus a star. We need to capture the probability of each data point. We can use a very clever way of rearranging this idea. If I take the product from, say, from I1 to n, this is what I guess. This is my sigmoid function outcome. I'm guessing the p. Taking the exponential part to 1, if the actual label is equal to class 1, for example, this is one of the class. If it isn't, this value will be 0. So it's not 1, this will be 0. But if it is 1, that will be 1. Now the other part is the same. If the class, actual class of y, it isn't 1, I mean the other class, in other words 0, maybe minus 1, then this value will be 1. Otherwise, it will be 0. So this can be 1 or can be 0. This is my guess. And this is my guess. Now, the point is, if I am guessing right, very large probability that this point is belong to a certain class. And then I'm looking at the actual class, the same class that I guessed. If this really happened, it means this term is going to be 1, probability going to be very high. And then multiply that by the other term. Well, this is 1 minus whatever probability I have done here is going to be small anyway. And this term is not true because the actual point that I'm talking about is belong to this class. So this is going to be 0. Anything to power of 0 is going to be 1. So I will be maximizing by taking this large value. But imagine I'm guessing wrong. So I give a very small probability. Well, the actual class again belong to this particular class. So this value will be 1. And this power of 1 will be this value. And the complement of what I was saying here is a very large value. And all of it is going to be waste. What we hope for, in other words to say, we hope to maximize this probability guess as much as we can. Since we established the understanding of this, we can improve. Because if I have this n number of data point very large, this product gonna get very small. So what we can manipulate here by taking the log of this guess. If we do that, we will be able, from algebraic perspective, to manipulate this entire term. We have just established a great way quantifying our assumption of these alphas. Very good loss function, and it's a convex kind of loss function. And what does convex mean? Just to remind you, we call this is a convex because if I draw any line here, it will be always above the minimums or contained within the function. But if I would have something looks like this, this is not a convex, although convex at some line here might be convex with a local minimum. This will lead me to global minimum. So I hope now the reason we are using this loss function is quite clear to you. Now what we want to do, we want to minimize this error. This is where I'm going to take the derivative of this function. So first of all, we can look at what's called the gradients of this function. Seems I forgot this is minus, should be minus the log. This is very important. We can look at term by term. So if I just only take the derivative, first of all, of this term, and then I can also take the derivative of this term alone. Taking the derivative of these two terms independently will lead you to the following. That is, This entire thing we see in here actually is the first derivative or the gradient of the maximum likelihood. So this is the derivative in terms of the alpha vector. Maybe we can actually change this into a matrix presentation. This is going to be the derivative actually in terms of the alpha. A transpose multiplied by y hat minus y. If I want to follow the gradient descent, and as we discussed before, learning rate and number of iteration, this is exactly equal by taking whatever y hat that I guess minus y multiplied actually by the exact point, the xi point, and multiplied by the learning rate and subtract that from the actual value to see which direction you're going in. And then you have actually updated the term. Let's say, for example, I would have data looks like maybe this. I design this shape here, and if my data would look like this, again, I would have design a shape like this. But the point of what I'm trying to say is in here, the steepness of this S shape. Well, I can go as steep as I want. Well, if I'm looking at this shape, this is going to be quite a bit in the negative side. So it should look like this. Now, this is my alpha value, say, and this is my error. Well, if I choose a very negative alpha, my error would be very high in this case. And if I keep enlarging my alphas, the error is going to keep going down and down and down. We'll never reach zero, but seems to be forever. If I'm looking at the other shape here, if I choose a very large alpha, my error is high, and the more I drop down the alpha into the negative side, my errors go down. But where shall I stop? If I don't have a specific way of stopping, I will be ending up with this case where you can make it a steep. This is the actual loose function. What we can do, actually, we're going to add a regularization, the ridge and the lasso technique of regularization. Let's say, for example, I'm going to use the ridge regularization. Look at this alpha. By adding this term, every time I do that, look careful what's going to happen with the alpha. It's going to look something like this. So again, somewhere around here is the best way to stop. Also, the other side of the equation, by adding this term again, this regularization is going to make a huge sense. But one more thing, maybe for this term, let me write again, if I'm talking about alpha 1 here, since we have just added this term, the derivative of this term you should be quite a bit familiar with. It's just 2 multiplied by actually lambda alphas. That's it. I mean, it's not a big deal. So this is my stochastic gradient descent of actually minimizing or reaching out to the best alpha. But personally, from my personal experience, even I've checked out actually different references and I tried myself, which we're going to do together in a while, that I found that there is alternative method that really could be at handy, which is they call it the Newton method. It says if I'm trying to find the minima of a function, for example, let me just draw in 2 dimensions like that. Imagine I'm going to choose one point on this function, then I'm going to make a quadratic function here that is tangent to this point. I'm going to draw a tangent line to the minima of this function. Now this will lead me to a new point here. I will repeat the exact same procedures. So by few number of iteration, I will reach out actually to the minima of the original function if it is convex function. This is where we call the Newton method. When we are talking about actually maybe 2 dimension of, imagine this is my x1 and x2, I'm going to take an initializing point, maybe this point here, and then around this point I'm going to draw a quadratic form of another equation, and I reach to its minimum point. And once I am here, I'm going to draw again this as a function of few point. There is no specific number of iteration, but you will converge sooner or later as long as this is a convex matrix. So this is the point where we can utilize this method by taking the derivative of this loose function. And it turns out this function, it is actually a convex function. To update this alpha, the new update alpha, we'll take the original alpha and then I subtract that from the following. I will take the first derivative divided by the second derivative. The first derivative is already, we know, A transpose the y hat minus y. Now the second one, it's a derivative of this one. Now if I'm not going through the details, but it turns out this going to be again A transpose some matrix, let me call it B, maybe A. B, it turns out to be something called the Hessian matrix, which is a diagonal matrix. And what is in every entry of these diagonal is my probability multiplied by the complement of that probability. What is the size of this matrix? Of course, this first entry will correspond to the first data point, the second to the second, and so on to n number of point. What we can do, we can actually transferring this into a multiple dimension by saying, well, and next, we're going to actually implement all what we have done so far using Python and try to visualize the problem in a better way. Now, if you look at the data set, how it's been graphed, it's obvious a linear implementation of data set is not going to make sense because we could see that the two labels are overlapped. So let me actually implement the line now, as I have done earlier. It is obvious now. This region here, we have a mixture. The labels are overlapped, represented using the logistic regression where all could be actually on that S shape. Everything above there, one class, below another class. So the implementation for the logistic regression, I have created an illustration of different alphas of alpha 1, alpha 2, just for this particular example. And then I create an A matrix that have x0, and then we have x1 and x2. Every point here is 1, and then this is the value of x1, x2, like that. So why I did that, because if I multiply this by the alpha vector, so it's going to be alpha naught plus, then alpha 1, x1 plus alpha 2, x2. So this is the linear combination. I'm going to pass a line space of possible values of alpha 1, like 100 values of alpha 1, and another line space maybe of another 100 values of alpha 2. And what I did, I took every value of alpha 1 with every combination here. So we got like 100 by 100 then possible combination of alphas. Now the initial value of alpha, it will be dependent on this line space. So this is complete illustration. I might be completely wrong of choosing this line space at the first place, but still I will be able to see some sort of convex like this, where the idea, I just want to show you, we are trying to find the minima, hoping that the good alphas are somewhere inside this combination of two line space. So basically this function does that. And then I create another function I call it prediction, function with the alphas. And basically what it does, nothing special, but it take actually every vector of alpha multiplied by the matrix that I have just created. And then I take this y guess and I pass it to the sigmoid function. So I would have the probability. And based on this value, I would make a prediction. And then I'm using this the simple form of error of the loss function. Then I graph everything. So if I run this one, this is my possible alpha 1, possible alpha 2, and I fixed, by the way, the alpha 0 to be just 0.3. You can change. So we're trying to find the minimum value in this particular space, right? You will find one which is correspond to this term error 0.45, and it tells me, well, if you look at these vector alphas from the combination that you have, this is the best vector alpha with the minimum error. But this is not the right strategy. So the right strategy, what we want to do, actually, we want to follow the minimization technique by choosing good alphas. So I've created this class here called Logistic Regression class. And actually at the same time, what I did, I imported from the sklearn Logistic Regression library. So I'm going to test this built-in library against the step-by-step technique we have developed. So in this class, in the instructor, just I'm going to receive learning rate and the iteration number. And inside here, there are a number of functions. The first one, I call it the fit function. So I would have the training data or the data matrix, whatever you call it. And I would have my vector of initialized vector of alphas and of course the alpha 0. I'm going to go through the number of iteration and every time I'm going to update the weight. So what is this update weight? It's another function, and I split the data set into actually one thing. This is the right approach. I using cross-fold if you like, or normal selection, random selection of the training dataset and test dataset. And finally, I'm using my model, first model called Logistic Regression, which is this class that I have just created. This is one model, and the other model is using the Logistic Regression from sklearn. And just to compare both them, what it would look like. And we compare, we see our model have done 53.7%. is poor, actually, using just only this simple way of leniency. It can be, of course, improved. Maybe you can change the learning rate, the number of iteration, etc. But I think you try on your own, and you will see that the best you can get maybe 60% or so. And using the sklearn built-in logistic regression function, which has some regularization correction of 77.6%, way better than this. But then I implemented the Newton-Raphson method, which we've been talking about, this guy here. So I take the original alpha, then the Hessian matrix inverse, multiplied by the gradient, the first derivative. So basically, it's nothing special here. This is the Newton operation, just taking, you can see maximum iteration, maybe I can stop after a while, and the tolerance, where shall I stop? If you're not careful of number of iterations, you might end up in a mistaken error, because the Hessian matrix expect this B matrix we were talking about to be diagonal and it have a determinant. If you reach converge, this matrix will be singular, so you will run into an error, which I ran into. So that's why I ran here a condition. I said, if the determinant of this matrix, it isn't zero, what I want you to do, I want you to do the first gradient and then the second derivative, okay? And then you make the update of this dp. And also, if I pass this, I'm going to ask the tolerance. If I am getting a value less than a specific, like tolerance number, very small, close to zero, also I want you to break and stop iteration. And let's try actually to run this Newton method. And you could see I have got 79.5% actually accuracy, comparing to the built-in function 77 of ASCII-learn. So using Newton method, it's proven really to be really, really good. So this is the bias alpha 1 and this is the alpha 2. Next, we will be looking at a problem when you have actually not only binary classification, but multiple class, like more than 2. The good news, nothing is going to be different from what we have learned. We will just generalize this maximum likelihood and then again take the derivative in our own way. Basically, most of the examples we have taken so far, when this y had possible binary, 2 possible outcome. And then we discuss, of course, when this binary it's linearly separable, and then when it is non-linearly separable, when we had to use the sigmoid. Now, what we want to do, actually, we want to take this one step farther, and by assuming y, it doesn't have only binary possible outcome. It could be as many 1 to 2 to 3 or k number of classes. And of course, you can think of this problem once again from a linear perspective or maybe from a nonlinear perspective, another word to say. In this case, it is some kind of a linear separation between these classes. There is much more complex problem when actually these classes are all just overlapping each other. I'm going to show you actually the technique which works very well in this case when the data somehow separable, maybe a little bit overlap, not too much, but I have chosen a really complex data set. Data point are really overlap. So the basic idea is first of all start with the first step. Are we going to make any changes into this sigmoid function? We will still stick with the same idea of taking f of x. We sigmoid that. This is for sure. By the way, just to confirm one important thing, maybe I missed to say previously, that in some books that they write down equation looks like this actually. Be sure this means the probability of y hat is not equal to this class we're talking about. It's the complement of this one, just to clarify mathematical intuition to that. All right, how about our loose function? We're going to still actually some sort of relying on the maximum likelihood cross entropy, the minus log, whatever you call it. But the point is that that was our loose function when we have like only 2 classes. But we're going to see that we're going to generalize that model, make it in multiple class. What are we going to do about that? But for now, I'm going to still actually relying on this. It's going to be about number 3. We need to take the derivative in terms of the alpha. Let's actually call this is alpha naught and this is alpha star. All right. I'm going to introduce you to something called the softmax. Let's just assume for assumption that my label 3 different possible labels. Now the procedure is going to be the same. So I have now probability, which we call it the loop gate. Before we go to the loose function, etc., what we're going to do actually, we need to learn something called the softmax function. Could you tell me this y vector, what it looks like? 0, this class maybe 2, this class is 1, and so on and so forth. We have to transfer this y into something called hot coding. If this value is taking place, we're going to fill it with 1. It means the other didn't happen. The second one, class of 2 is taking place. So this is the class of 2 that I put 1 here and 0 everywhere else, and so on and so forth. This transformation we call binarization. And why is that important? Because if I want to look at y now, I am actually able to deal with y at 3 different status. All the classes of y were equal, for example, to 0. The data point when y was equal to 1, and all the data point when y was equal to 2. Imagine now I have 3 different data sets I am dealing with in this case. Now, the idea of multi-class and logistic regression is to design alpha vector that can guess if my class is 0, and another alpha vector can guess if my class is 1, and another alpha can guess if my class is 2. It's a kind of enhancement on the framework. It is not something new. Even mathematically, it's not something like that much complex. But the point is here, my y hat will have 3 different values, right? Because we have one set of alpha here, one set of alpha here, one set of alpha here. So corresponding to this alpha vector happens to be, let's say, -1, for example. Okay, the other one maybe happens to be 0. I'm talking about the linear equation alone before any sigmoid into it. And the last value was 2. So I have 3 different y hat based on 3 different alpha vector. Take e to this value here and e to this value here. So e to power of -1, e power of 0, and e to power of 2. Something like that. And then I'm going to calculate the probability of phi is equal to 0 given that x. That will be e to power of -1 divided by the sum of these 3. And the probability of y is equal class 1 given x. Again, it's e power of 0 divided by this sum. And same for the third one, or y is equal to given x. It's just equal to e power of 2 on that sum. You will find one of them have the highest value. And one interesting thing that the sum of these 3 must come to 1, just like a probability. So what I'm going to say, we're going to take the largest value among these 3 possible outcomes, and we'll say, well, I guess the class is going to be this one. If I have done an error, this is where we're going to go and do the third step, of course, to learn these alphas as best as I can. That is the entire idea of multi-class logistic regression. Let's go ahead to Python and try to implement the data set. Now, if I graph this data set, there are 3 classes here. You can see 0, 1, and 2. This is a very, very complex situation. And you can see the counter of y that class 1 have 334, class 0 have 332, and class 2 have 334. So these are the 3 classes of y. And then we're going to do the step of encoder. So this is one class, actually. It was class of 1. This was a class of 0. This was a class of 1. This was a class of 2. We're going to prepare these 3 important functions. First, called predict function, sigmoid, lose, and then the gradients, and then the bias. Finally, the update. All these you should be familiar with. By the way, I'm using gradient descent. You could try on your own using Newton. So in this classification report, you could see our accuracy was 44%. Quite poor, not quite actually much of a poor. But when I did the logistic regression, the built-in by the sklearn, it's a 43%. Well, still the same performance. You see, whatever you try, you're not going to get better. The data need really to be enhanced again. Maybe we need to make some transformation on the X. But again, I mean, the both performance you could see is quite a bit close to each other, nothing special. So that was all the idea of multi-class prediction using logistic regression algorithm. We should be able to proceed, have a quick look at the key nearest neighbor algorithm. That's exactly what I'm going to do next. I will see you then.